evening, ladies and gentlemen, and welcome to the beautiful auditorium at the Albright Knox Art Gallery. Thank you so much for being with us tonight. It's a little nippy outside, but it's warm and toasty in here. My name is Jack Walsh, president of the Darwin Martin House Board, and I'd like to thank in particular the gallery for the use of their auditorium, to Board Chair Charlie Banta, to Executive Director Louis Grachos and their wonderful staff. Thank you for an extension of a partnership that began back in 2003. Toshiko, it's hard to believe that 5 years have passed since the gallery's exposition and symposium Mori on Wright, Designs for the Visitor Center of the Darwin Martin House. That exhibition 5 years ago was a collaboration among the Martin House, the Albright Knox, and the UB School of Architecture and Planning. We've all aged a bit gracefully, I hope. And we'd like to thank both the gallery and the school for their generous support of tonight's panel. We thought that in this election season that you'd enjoy a little breather. Tina Fey, as good as she is, can't hold a candle to Toshiko Mori. And tonight's moderator, Brian Carter, actually taught diction to Jim Lair, Gwen Eiffel, and Bob Schieffer. You will learn nothing tonight about subprime mortgages, the effectiveness of the surge, or the struggles of the middle class. But if you pay rapt attention, you may come away with a profound appreciation of substrata, how architecture and engineering do merge, and the intricacies of some very special glass. The title of tonight's lecture and panel discussion is Integration of Architecture and Engineering in the Eleanor and Wilson Greatbatch Pavilion. We'd like to mention that for any architects who are here tonight who would like continuing education credits, there are forms at the front of the auditorium, and please see Kathy Hayes if you have any questions about getting proper credit. Our Visitor Welcome and Interpretive Center is currently under magnificent construction at the Frank Lloyd Wright Darwin Martin House complex, just a squash-colored bricks toss across Hoyt Lake on Jewett Parkway. It's on schedule for substantial completion by the end of December. We are very excited about this truly remarkable building, rising in such beautifully sensitive design and scale and juxtaposition to our Martin House campus. And we are all equally excited for Buffalo and for the rich promise of expanded cultural tourism and economic development in partnership with vibrant programs like here at the gallery, which the completed Martin House will offer our community. If you've not done so, please visit the site, take a tour of the Martin House, and see for yourself how interesting and intricate an historic preservation and restoration project can be. It's now my pleasure to introduce our speakers and panelists, and I've been asked to give you a little background on each. I would ask if briefly when I call your names you might stand and face the audience for just a few seconds so they know who you are. I wanted to tell you that I've been informed that none of these people wishes to run for President of the United States. That's good because I went to school and played baseball with and know President George Bush, and you, sirs and madam, are no George Bush. Each of our four panelists will talk about their part in the project, and then Brian Carter, Dean of the UB School of Architecture and Planning, and a pearl of great price, will field your questions. The Phillies and Devil Rays are proudly offering their lineups tonight in the first game of the World Series, but we too have a murderer's row of talented swingers on our team. Toshiko Mori, Toshiko, if you could stand. Toshiko Mori was selected as the Visitor Center Architect during a 2002 design competition, and her submission was one of 5 designs submitted, and all were on display here in that 2003 exhibition here at the gallery. The Robert P. Hubbard Professor of Harvard's Graduate School of Design, Toshiko was chair of the Harvard Department from 2002 to 2008. She taught at the Cooper Union School of Architecture, her alma mater, for 12 years until her tenured arrival at Harvard in 1995. Toshiko has received countless honors, including the Academy Award from the American Academy of Arts and Letters and a Medal of Honor from AIA. She established Toshiko Mori Architect in 1981 and is its principal, famous for 20 years of innovative and influential work for residential and institutional projects. Her 2008 awards include special tribute for her Syracuse Center of Excellence and her addition to the Paul Rudolph House in Florida. I'd like to also mention that Toshiko has just completed, not yet on the website, the beautiful Humanities Center at Brown University. Toshiko is recognized for her intelligent approach to historical context in all her work, ecologically sensitive siting strategies, and innovative use of materials that creatively integrate design and technology and which are both spatially compelling and pragmatic. For the Greatbatch Pavilion, Toshiko's design aimed to project a clear, coherent identity that completed Frank Lloyd Wright's work without competing with its design. If she were president, Toshiko would no doubt deliver a compelling design for our future. Dmitri Jajich is a project engineer from a Skidmore, Owings Merrill Chicago office and is engaged in the structural engineering of the Greatbatch Pavilion. He works with architectural and building service teams to ensure that structural engineering design concepts are within project requirements. He oversees the preparation of the complete structural engineering documents for proper compliance with the approved program and is professionally registered in New York and Illinois. Dmitri received his BAs in both physics and in art history from Macalester College in 1997. Straddling the vibrancy of Grand Avenue in St. Paul, Minnesota, Macalester is also the alma mater of former UN leader Kofi Annan. Dmitri earned his Master's of Science in Civil and Structural Engineering from the U of M in 2000. Go Gophers. His firm has more than 70 years of expertise as a multidisciplinary firm of architecture, urban design and planning, engineering, and sustainable design. Its over 900 design awards are more than any other firm in the U.S., and it has offices in Chicago, New York, San Francisco, Washington, LA, London, Hong Kong, Shanghai, and Brussels. Dmitri, were he president, would offer less stress in our lives and would introduce us all to Fritz Mondale or former Governor Jesse Ventura, as you might prefer. Paul Kreitler. Paul is the mechanical consulting engineer on this project from the Landmark Facilities Group. He is an expert in the design of specialized mechanical systems for climate control and preservation in historic facilities. Since 2003, Paul has worked in a red state and headed the Columbus office of Landmark's work. His BA in civil engineering is from Vanderbilt, and he earned his professional EIT designation in the year 2000. Paul's work has been invaluable to us in designing the geothermal well exchange climate control system for our historic buildings, as well as the restructured pergola, conservatory, and carriage house. He has supervised more well drilling than Mobil Oil. He and his firm have a national reputation for precision climate control, for preserving art documents, objects, and furniture, as well as the special buildings that house them. Much of Paul's work naturally revolves around the museum community. Were Paul president, he would no doubt deliver an environment of clean air and a proper balance of dry and moist comfort. He'd be a great choice as Secretary of Ideal Exteriors or Interiors. Bruce Nichol. Bruce is the founding partner of Front Inc. and brings 20 years of specialized experience to Toshiko's team. In particular, he has consulted with Toshiko on our dramatic glass curtain wall that will enclose our building on 3 sides. Bruce is an expert on exterior facades, skylights, glass screens and floors, and interior elements from design concept to project completion. He is licensed as an architect with the Royal Institute of British Architects in the UK, is registered with the Architects Registration Board, and is an international associate with AIA. His professional experience includes high-rise construction, international airport and transportation projects, and prior to establishing Front Inc., the design and facade creation of the New York Times building while a member of the Renzo Piano Building Workshop in Paris. Bruce earned his BA honors degree from Huddersfield Polytechnic and his graduate diploma in architecture from Oxford Brookes University. Bruce and his colleagues work in New York City. His custom curtain wall and structural glass expertise have greatly assisted this project. If United States law permitted his election to the presidency, Bruce's leadership would help us all see the future clearly, dryly, safely, and warmly. Brian Carter, our distinguished moderator, is an architect who has practiced with ARB in London prior to chairing the architecture program at the University of Michigan. In 2002, Brian was appointed Professor of Architecture and Dean of the School of Architecture and Planning at UB. A designer of numerous award-winning buildings in Europe, he is also an author of books on modern architecture and has been curator of exhibitions on the works of the engineer Peter Rice, designers Charles and Ray Eames, and architects Eero Saarinen and Albert Kahn. Having skated for 4 years, had my nose broken, and received the Team Doctor's Award for most stitches in Yale's Saarinen hockey rink, it is bloody good to see you tonight, Brian. Brian is a member of the Royal Institute of British Architects and a Fellow of the Royal Society of the Arts. Brian generously serves on the Mountain House Board and works tirelessly to promote the architectural scene in Buffalo, hosting leading architects at UB's School of Architecture Speaker Series. He is particularly excited about the remarkable new buildings that are gracing this city and their significance. He is very good at the work he does. He loves his present work at UB and would not serve as president even if drafted. Brian will field your questions when our panelists have concluded their individual remarks and will tell you briefly about our roles of engagement. Before we begin, I'd like to recognize Howard Zemsky and Robert Joya, predecessor chairs of the board of the Martin House Restoration Corporation. I don't know if there are other chairs of the board like Charlie Banta here, but if Howard and Robert would please stand. Thank you all for being with us tonight. Enjoy this evening and our wonderful panelists who are so gracious to be here with us. And Brian, the floor is yours.
So we're delighted to have a multidisciplinary team of designers here and realize that very often the discussion about architecture is directed through architects. And we all know that it takes many people to make buildings, and so the opportunity tonight is really to have that discussion and to hear about the roles that people have played in the building. And it seems that in this particular project, when Wright talked tirelessly about an organic approach to architecture, which he went on to explain as meaning that things were integrated, systems were integrated, that things did more than one job in the project. That Toshiko's project and having the team here tonight who've really reinterpreted that in a new building is something which is a really special opportunity for us here in Buffalo. I would argue that actually this project is unique, not just in the region, not just in the country, but internationally. And I think there are lots of things which are hidden in the project and that one never hears about those. And tonight really is an opportunity for us to hear about the contributions that everybody has made to make this project an outstanding project and a really integrated project. So I'd like really to welcome the speakers. I'm delighted that everybody is being able to come here. It's organizationally been difficult in terms of people being here, there and everywhere, and I'd like to acknowledge Mary Roberts and her patience. This was a sort of idea which emerged over a cup of tea and a crazy discussion, and here we are, and everybody's here, and I'm delighted that you've been able to come to the meeting. Certainly for everybody in the community, I think for students in the program in architecture and planning, and for people in the profession, there's a need to think about architecture in this sort of deep way. So I really would like to welcome everybody here tonight, and I particularly welcome the speakers, and I'd really like to invite Toshiko to speak and lead the batting, and I'm not running for president.
Thank you very much, Jack, for amazing introduction. Like Harvard, I don't know what it is about presidents of Darwin Martin House. I think you do amazing acts, and it's hard act to follow for anybody after that. And also in terms of president, I'm not running for president, but the one I think should really run for president among all of us is really Mary Roberts. She has a capacity and patience and integrity, understanding, and just it's a very difficult project, it's very challenging, and just calmness which pervades us all. She makes us feel it's going to be okay when we are complete panic, and she just has this caliber, or presidential caliber amongst all of us. I just have to thank you especially about that. And also, this is a very rare forum. We are rarely asked as architects to talk to public audience about the project and process, and especially inviting consultants to talk about the story behind the scenes. And what you see is usually the building, and there's a lot of stories behind how Frank Lloyd Wright had worked with engineers and so forth. If you go to University of Buffalo archives, or if you see Jack Quinner's book, you understand and read it. But this is a rare occasion in which we can talk about the project in process. So that's very important. I really appreciate very much Albright Knox Gallery to invite us to form this forum, and also for Darwin Martin Administration Corporation to arrange this. So I really thank you very much. And one of the reasons why I'm so happy about it is that this is a really collaborative effort with architects, engineers, consultants from the very beginning. And inherently, this project, as Brian has expressed, is integration of disciplines. We really follow organic architecture principle of Frank Lloyd Wright. It's just not a romantic notion of integrating nature and artifice. If he were alive today, we imagine he would work this way to make use of sustainable technologies, to use the cutting-edge technology and technique to deliver the most efficiently functional and beautifully integrated building. So it was always the big Frank Lloyd Wright was back of our head, but we think of Frank in 21st century. So that's how we approach this as a team. In terms of also partisanship, I have to confess that in our disciplines, there's a lot of breaking off into splinters. Some facade consultants will do something, mechanical consultants will do something, structural designers will do something, architects will do something, and sometimes I would say majority of projects are much more isolated discipline. Architects will form a discipline, and everybody else kind of follow. And sometimes consultants don't even get to meet each other or talk to each other. This model was very different, and that's what's unique about it. And we got together in the beginning, we kept conversation going, consultants talked among themselves, and in a dinner discussion we were just talking, America is a very litigious environment, so that because of insurance and lawyers, a lot of times we are not even allowed to talk to each other so that they know who to sue you. That's the environment which really is a negative environment to promote collaboration. So yes, of course, we risk a lot, and all the consultants are saying, yeah, it's all going to be in Toshiko's insurance, who cares, we can talk. But at the same time, this particular client, Darwin Martin Restoration Corporation, and the community around it, we think this is the only way. Yes, we are risking it, but risking with a very careful calculation, integrating discipline to deliver a building which is efficient. And the project is under 8,000 square feet, and it's $5 million. And I think we wanted to best use of every penny of $5 million. So this building is an incredible performance. So that's the kind of backstory you hear tonight. And to go into a background, I just described the beginning of this. Darwin Martin House, Frank Lloyd Wright, 1903, 1905. The plan of a compound of Darwin Martin House is described by himself as opus. He really loved this plan. He had this plan next to his drafting table for the rest of his life. So it's a pride of his legacy, this particular plan. And then located in Parkside neighborhood designed by Olmsted. This is a very, very interesting juxtaposition, I think, to have a pavilion next to this masterpiece, but also integrated to the neighborhood. And in terms of that, we have located this narrow edge to face this particular garden. So pavilion is really addressing the garden itself. When you see this building now, you will really see it because the glass is crystal clear. You kind of see right through it. So it's really idea of anti-building as opposed to a very positive building of Frank Lloyd Wright. This is the site. And as a reference to this, and also to strengthen the concept of garden pavilion, we have taken a module of pergola, it's about 7'7" and then projected it and made it into a structural module and also glazing module of the pavilion itself. In pavilion proportion size is approximately, it fits in like this here, and this particular central area is also reference to that, and there's a lot of reference within that. As an architect, went back and forth as if you are having a dialogue with Frank Lloyd Wright. This is what he has done now, what will be, what he has done then, what will be now. And also in terms of bit of a chess game, if you move solid brick, I will move into clear, transparent glass. If he would do a hip-proof, reverse hip-proof, to note that it's a public building, and this is Darwin Martin House is a house, a private residence. So there's kind of opposite strategy I have deployed throughout. The building are linear and low like this, and it's diminutive, very small, as opposed to rather massivity of Darwin Martin House. So it's also playing an opposite role, and idea is to have its own presence, but always respectful of a Darwin Martin House itself. And in a central, one of the most interesting aspects as an architect for Darwin Martin House plan is that it's the beginning of what you call open plan in 1905, which is that there are no walls really, and it's all columns and piers, and we call it open plan. It makes space flow. It's a very important principle. It's an incredibly progressive principle. And then also notion of cantilever. Again, he used steel in a structural hip roof. Again, very progressive concept of it. And if you see a Darwin Martin House, you see these piers, which is part of a structure and also infrastructure. It had conveyed then the gas, later electricity. It had heating system in it, and also it has some bookcases. So it's a multifunctionality of architectural elements is something which is deeply embedded within the Darwin Martin House itself. So these are the piers. And this is, in fact, the current plan. We have gone through evolution of thought process, and we have decreased some. For example, basement is cut out from a project, but we have integrated exhibition on the ground ground space. And people who remember the original scheme, we had entries coming from here, but we were able to have a vestibule toward the west wall, so that sequence you enter here, you will have a ticket booth here, and you have a display, a film display here, exhibition all throughout, and also digital interactive display here. And then you will go out and then go visit Darwin Mining House. So that's the current way of circulation path. Originally, this was a concept we had, and which also we kept together, is that 4 piers are primary structural elements which supporting a cantilever. But Dmitri will tell you the kind of trick we played with this pyramidal column, which is kind of really interesting. It appears to be cantilever, but these tiny little columns are also supportive of a structure itself. So it really appears a cantilever, but it's really not to an extent. It's a long span supported. So the appearance is integration of structure and curtain wall itself, and that's actually again a lot of going back and forth has gone back with the architect, structure engineer, and facade consultant in glazing, and in terms of figuring out tolerance and so forth. In terms of mechanical engineering, at competition phase and later on, climate engineering concept is proposed by Transolar, Matthias Schuler of Stuttgart, and we wanted to embrace sustainable strategies. One is that it's going to have radiant heating and cooling system embedded in the floor, and there's geothermal wells. And we have a solid wall in the west, which, if you know from this area, prevailing wind comes from Great Lakes from the west, so that this wall creates a thermal mass to protect the pavilion from a cold wind. And so that it's a very natural siting to have a solid wall on the west and clear glass on 3 other sides of a glass. And the roof also here is designed to hold snow load. I think Dmitri can explain. He's actually tripled the requirements, load and so forth. And also, we know Buffalo, you have a lot of snow. And the concept was that snow will act as a possible insulation layer when there's accumulation, but for a drain, which is in the piers, we actually have heat trace in it, so that ice gets melted and then get drained through the piers inside. And we come up with a displacement ventilation. It's a system also Paul can describe in detail. There's no ductwork at all. The entire air is moving with a convection system, naturally moving, very comfortable. And also to accommodate different populations. Sometimes there's nobody, sometimes 20 visitors, 60 visitors, 210 people. And there's CO2 sensors in which it senses what kind of occupancy it is, and then the system responds accordingly. So again, it's like a building breathing. It's another one, responsive building, which is organic principles according to it. Also, the slope of a ceiling is so that you get daylight bounced off inside of it, and most of the time the visitor center is open, that you don't need artificial light at all. So it's really promoting natural lighting as much as possible. And what I call snow light is daylight reflector. When there's a lot of snow, which we think about that in Buffalo, although in 5 years I have been here, I have never seen a snow. So, but I'm trusting people are telling me there's a snow. But the idea is that when there's a snow, you do have heat and light bouncing into it, and there's in fact a heat gain in this pavilion, which is very welcome in coldest time. And then that efficiency absorbs the system, so there's less heating is required, and so forth. So. And that's a geothermal well site plan. It's one of the reasons for geothermal plan is also sustainable. It's tapping into the ground temperature about 47 degrees constantly. So you just heat a little bit or cool a little bit. You don't have to cool that much. And also it's quiet. It's in a residential neighborhood. There's no condenser making huge noises and so forth. So that was at most of important for us in terms of acoustical quality that we give to the neighborhood, as well as to the quality of energy delivery, and then also Martin House to be self-sustaining in terms of operating these facilities. And geothermal system is also for the Darwin Martin House itself. This is a crazy diagram drawn by a subcontractor, but conceived by Landmarks. And we have two systems, which is radiant flow system, which gives you constant heat, but very slow. So most of the time, building operates in radiant cooling or flow, heating mode. But then forced air system takes care of a large load of more people, big events, very cold weather. And he can go into details, but all these little wigglies and little spaghetti is so that more turns air has to make, it has to operate quietly. So the acoustical issues are concerned here too, this radiant heating. Also working with lighting, ARB lighting, we have come up with a strategy which does not have any overhead light, and it's all reflected off the ceiling. It's very soft light, but you can see perimeter. And then as you can see, we have done a lot of simulation. The contemporary technology allows us more to predict what happens. So in order to design this entire building, we use a lot of three-dimensional imaging or three-dimensional simulation technique to really foresee the performance of each component of building, which you'll see by many of them showing you animation, simulation techniques, and so forth. So that's the building itself. And that's what's happening. And we'll go a little bit about this west wall, which no one will talk about. So I don't want my west wall to be an orphan child, because it's a concrete wall, not a glamorous glass wall. But it has a role to play, which is, as I said, that this wall is preventing from wind from coming in. So in a sense, it's really protection against it. And also, it has this shelf cantilever, which is very similar to a cantilever of a second floor of a Darwin one. There's about equal distance of setback here. So in a sense, it's a back wall, but it also has a meaning about how we are dealing with this. And this is a put-in-place reinforced concrete wall. It's multitasking because it's insulating and also protecting against west wind, but also it has fresh air intake in it. And then also visually, it imitates the pattern of a facade. It's like a palimpsest or memory of a Darwin Martin facade itself. It's cast in place. And it looks very clean and easy, but it's really not. You see that little shelf here. That's actually funny. You see the glass wall here from the ceiling, and this particular one gives this shaded elevation in the back of it. So I recommend you walk around the back also and take a look at that too. To achieve this, we have gone through about 8 different mock-ups of this, different releasing agents, different mixing, different vibration methods, and so forth. So it's really taken a lot of time to make this patterning right and precise measurements of, and as you can see, this was poured in one day, 100 feet long wall, and they are pouring, conveying it very carefully, horizontal layers, and he's vibrating as you go along to just give it an evenness of it. So to just get this process right was amazing collaboration on site. And I have to say also, yes, we have architects and then consultants group, but Chimileli has been phenomenal in organizing this entire project. And you have in this area, subcontractors have been terrific. I think we, at this moment, are really getting a world-class quality building. We are very, very happy about it. But the people on site are working very, very hard. And this gets to be very meticulous, great, really sophisticated concrete finish to the back wall. Again, this is also a facade we thought about, but it's not usually featured as something. So it's kind of, this is a wall, and that's the Darwin Martin house. So we got the exact same dimension here. If you see the corner of this wall, you really see the same profile, deep recess that Frank Lloyd Wright made to make sure brick look like they're floating. So this is the kind of detail we've reflected on it. In terms of precision, steel column you see is 2 3/4 by 2 3/4 stainless steel solid. It was CNC milled, and then this is going through Madison is a grinding system, which is trying to make it absolute 90-degree corners, and also to grind out any pits and so forth. So it's kind of going through. So it's a really beautiful, incredible, precisely cut steel column, and it's very slender, and the slenderness is possible because it's spaced about 7 foot 7 inches. Spacing is quite narrow for steel. Instead of having 25 or 30 feet dimension to have a big fat columns, we have come up with strategies of having smaller columns in repetition, so it kind of blends into, it's kind of idea of, it's there, but it disappears at the same time. So that's actually how the steel column is all supporting here. Dmitri will go into details, but also it's helping with a cantilever to make it more of a long span than cantilever by supporting the different elements. Bernie Wagner, I don't know, are you here? He's a photographer who's been photographing this project on a daily basis, so we are beneficiary of showing you nice snowy day. They started the work. He's been just photographing daily or by every few days. It's just we have this incredible photography log of a project, and excavation is happening here. And for excavation, we had to use a method called vertical trenching to avoid excess vibration, to protect the neighbors and also to protect the historic building of Darwin Martin House. There's monitors installed, so there's sensors there. If we just make alarm, if there's too much vibration, we were able to avoid all of that. So more digging taking place by making a formwork for west wall here. And basement, where there's a mechanical system being completed. And then they are putting a reinforcement for perimeter wall here, and they're pouring a perimeter wall, and then the west wall basement is being completed, and starting a dig holes for the 4 piers in the middle here, and this ductwork is being installed below grade, and more squiggles to go into air outlets, inlets, and 4 piers. Steel is being constructed as you go. And as you see at the same time, west wall is being completed as you go along. Slab is being poured. More and steel construction framing is going through. This is completion of steel framing for the roof. I suggest you take a look because this is going to be hidden all the time. And this white thing you're seeing is really a roof drain that's going to be connected to the piers, one of the piers here. This is all roof drain coming through. This is insulated so you don't hear the noise of rain or water being melted. And you see a skylight in the middle here like this, and that's being installed to give a daylight throughout. And this is a photograph of a crew, subcontractors installing glazing on above the west wall. And this is in process of glazing installation. And it's quite an operation because some of the glazing, triple glazing, about 3¼ inch thick, 15 feet high. The biggest panel is 8'4", some of the biggest glazing panel probably in North America. And when I talk to glaziers on the site, he says this is about the biggest piece of glass they have installed in their life. And he's been at it for 30 years or something. So it's quite something. And it's a very precision is important because some of the tolerances, especially north, went up to only 1/4 inch tolerance. And this glass is very delicate at this point, but once it's installed, it will be incredibly sturdy. You can't run the trucks across it. If you try to kick it, you're going to break your toe, so please be careful about that. It's very hard. So this is being installed, and I have to say they have done it very quickly. It's completed now, and we had record of no breakage coming. These are manufactured and assembled in triple glazing in China, shipped, 0 breakage, shipping 0 breakage on the site, which is unheard of. This is like really amazing record. So this is end of my talk, and I will just give my podium to Dmitri, who will talk about structure.
My name is Dmitri Jajich, and as stated before, I'm a structural engineer with Skidmore, Owings Merrill. And my firm is best known for engineering super tall buildings all over the world. And it's worth mentioning this briefly because engineering the world's tallest buildings is clearly a challenge because of their scale. But it's not an exaggeration to say that more difficult than that is integrating architecture and structure when you design some of the world's tallest building, because in this case the structure can't hide. It has to be integral with the architectural concept, and we have to work very hard and very creatively to come up with a structure that's not subservient to and hiding from the architecture, nor is it dominant, unsightly, or unattractive. And so really those concerns that are always a concern with super tall buildings were very much a part of the design of the structure of this new pavilion, because really there's no place for the structure to hide. It's part of the architectural expression, and we needed to come up with something not only economical and efficient, but also evocative and hopefully elegant. So this quote may seem a little haughty, but it suggests that an analogy that if poetry is economy in words, that the art of structural engineering is the economy of structure. And I think it's true because when you strip everything but what is required, you often come up with something that can be very evocative and beautiful in its own right, even if that pursuit starts from a purely practical and utilitarian point of view. An example is this dirigible frame, and I think we can assume that the engineers who worked on this had one concern, and it was to make it as light as possible. And whether through trial and error or through genius, whatever they came up with in the end, I think is a very beautiful form in its own right. One of my favorites are these agricultural irrigation trusses you see throughout the United States, and unquestionably they were designed to be as cheap as possible because they had to span long distances of farm fields and be affordable. But what the result is, again, either through a brilliant engineer, but more likely just through intuition and trial and error, is a form that perfectly illustrates the underlying physics of spanning, and I find quite beautiful. Just one more example, a racing bicycle wheel, utilitarian, lightweight, but something quite attractive emerges. And these forms are come to with really no concern for aesthetics. Unfortunately, pursuing economy and least weight or material doesn't often end up with beautiful forms. We all know the world is full of efficient, practical, ugly structures. So the challenge as an engineer, a structural engineer, is to come up with a structure that is appropriate, efficient, and appropriate meaning it meets all the demands, which is, in a structural point of view, is usually it's strong enough, it's stiff enough, but at the same time is attractive and elegant. And hopefully, if we do our job right, we meet all those criteria. So now I'm going to tell you some more specifics about this structure and try to convince you that that's what we achieved in the design of this pavilion. I'm just going to walk through the structure from the ground up in a little greater detail than Toshiko did. And we start out with just simple concrete strip footings bearing on rock. And all a footing is it's just a hunk of concrete that distributes weight over soil or rock. And we're fortunate and unfortunate at this site to have bedrock. It's strong enough that you could build a high-rise building, which is great. It's not going to settle. But at the same time, it's difficult to remove easily. Moving our way up, we have the concrete walls that Toshiko already showed. And I'm going to pause here in a little greater detail. Because we wanted to have such a clear, unencumbered perimeter of the building, we really had to focus all of the structural lateral strength at these four central piers here. And in order to do that, conventionally we would have wanted to put X bracing across here to stiffen it up. That would have been architecturally and undesirable. So we made these cantilevers, and a cantilever is just fixed at the base, so all of the rigidity comes from this fixity here. So to achieve that, you can't just stick it into the ground like a fence post, because the loads are a little too big. So we actually have this frame of so-called grade beams underground that I think are almost 3 feet deep. And so underground here, buried, is a rigid frame that allows this column to cantilever up above the ground and be stiff enough. And on top of that, we encase the column in concrete, and by encasing it, you get much, much more stiffness than you would from the steel column alone. So just moving on our way up, the whole perimeter wall actually also bears on rock, so that the structure will not settle differentially over time. On the, let's see if I get my directions right, on the east side of the building is slab on grade, which is just concrete bearing on compacted gravel. And then on the west side, spanning over the basement, is a metal deck composite slab, shown in blue here. The west walls, and finally this perimeter of steel columns that I'm going to talk about in greater detail. Of course, the structural framing for the roof, and obviously this has to hold up the roof and snow loads, but it also defines the geometry of the roof, which I think is so important in the structural form. And the steel members are actually tapered to mirror and match the structural form of the roof, not only aesthetically but also functionally. The taper is helpful. Finally, there's a metal roof deck, which obviously supports the roof membrane, the snow loads. But more importantly, in our case, this deck acts like what we call a diaphragm as an engineer, and that is it transfers in-plane forces. And the reason this is important is because when the wind blows on the walls, there's no stiffness out here at the perimeter, so it has to travel, the forces have to travel through this diaphragm and get back to these four central piers where it can be resisted by the cantilevers. Finally, the perimeter glazing, which is not directly the structural system, but encloses the building and building. Let's see if this plays. This movie is an exaggerated deformation of the building under wind loads. I don't want to alarm you. I'm so used to seeing these movies that when I play them, I have to be reminded to explain that to people. But this is a several hundred times magnification. And it shows that as the wind blows laterally in this direction, the building tends to twist because the four central columns are eccentric and the whole building is not symmetric about the center. This red diagram you see growing and shrinking is the so-called moment diagram. It shows the degree of overturning in the columns, and the perimeter columns take none of that because they're so slender and flexible, and it all gets transferred back here. So that's how the structure will move under a storm wind load, but you probably wouldn't even be able to perceive it if you were there. This next slide is this is the fundamental mode of vibration, and every object or structure has a natural frequency, and the stiffer a structure, the higher the mode of vibration, and the more mass, the lower. And this is very familiar. It's a guitar string. If you add stiffness, the pitch gets higher. If you add mass, the pitch gets lower. A building is no different. And so if you were to pluck the building, as it were, this is how it would vibrate. And the fact that it's twisting is a result of not having perimeter bracing. So it's a little bit flexible torsionally, but it's stiff enough to be stable and strong and withstand earthquakes and wind loads. Some more movies. These movies show the deflection of the entire structural system under wind load from the four directions. Again, of course, exaggerated. And what I think is interesting that might not be obvious to everyone here is you see that under lateral wind loads, there's actually tremendous uplift. The roof actually tends to lift up, and that's the deflection you see here. And that's a more dominant response even than the lateral movement, which is what you might expect. So in a windstorm, if you didn't have the building tied down, the roof would rip off. So, finally, this is an exaggerated deformation under snow loads, and you can see that you're going to get large deflections in this very long span here under snow loads. Again, exaggerated. Finally, this is a plot of the axial load in the perimeter columns. And again, because the spans are different, this is, I forget, maybe 20 feet. Here we have almost 50 feet, and varies along here and varies in the corners. The load in each column varies. From a purely quantitative point of view, you could say an optimized structure would be one in which every single column was a different size to perfectly match the load. That would be impractical and aesthetically displeasing, as we want to see a uniform colonnade. So obviously we have to design our column for the worst case load for these two columns here, which support this long span girder. And the vertical load of the snow load is further magnified by the cantilever, which tends to magnify it like a lever arm. So this 21,500 pounds represents the load these columns would support on the day where you have 6 feet of snow on the roof that hopefully won't come for the next 100 years, but if it does, everything will be fine. And here's the result, which I think is rather impressive. We have columns that are about 15 feet tall, and they're only 2 1/4 by 2 1/4 inches. This formula here will be familiar to engineers. It's a formula for Euler buckling that a mathematician stumbled upon in 1751. And it says that the load at which a column will buckle is proportional to the stiffness of the column, and it has nothing to do with the strength. So if this column were to buckle, the material would be fine, the column would just elastically deform. And that should be familiar to anyone. If you tried to compress your car antenna, it would buckle, but then it would bounce back, indicating that you hadn't overstressed any of the material. And that's the failure mode for our columns, which is unusual in columns. Columns are usually much stockier, and while engineers typically try to avoid column buckling, as we do too. Since really, I mean, one of the design imperatives was to make this facade as dramatic and transparent as possible. So we really studied how a column buckles really carefully, beyond what you typically would do. And right here is the load. This gray line indicates the load at maximum code snow loads plus dead load. Moving up this curve, I'm sorry, this is the load in a column, and this is the deflection, how much it bows out. Up here at the red line is the load at which the column material would start to be overstressed. So even at 3 times the load it's designed for, you still wouldn't overstress the column steel, and you still would have capacity to hold all this load, even though the column would have been buckled. Typically an engineer wouldn't consider anything beyond that, and we're not actually counting on it, but it's nice to know that even if, I don't know, global warming causes a 20-foot snowdrift and the columns all buckle, they'll still hold up the load. Toshiko already talked about these columns, but I just want to stress that it's really unusual to have a solid stainless steel column. Normally we cover up our structures. Here even though it's minimized in size, it's featured, and it's a really nice architectural component. They were milled. The fabricator actually, when they looked at our drawings, they didn't even know where to buy these, and we had to encourage them. I did a Google search and found 300 suppliers, but they're unusual, and it's not typical to have solid stainless steel columns. So just in closing, I'll run really briefly through the construction photos again. I know you saw some before, but these are the strip footings on a rock. Starting to construct the basement walls. Here are the 4 piers again, and again you can see this rebar coming out of the ground, and these lines here, those are the grade beams below ground, and then all of this will be encased in concrete, and they'll bend these bars back up to encase that column and give it the stiffness it needs. Perimeter columns in steel. This is the cantilever Toshiko talked about, so these columns on the west volume are actually sitting on this shelf here. These long span framing. And you can see this is a 27-inch deep steel member that then starts to taper to a narrower profile out at the end. And that takes some extra work from the fabricator to cut and weld that all back together. Just a few more pictures how the sloped roof beams meet the square top of the columns. Roof membrane partially in place. Again, this dramatic cantilever at the north end and the slender columns. Some of the rather tricky detailing that was required to have all these members at different angles come together and sit on top of a very tiny column. And I think this emphasizes the scale of the steel beams compared to this really slender column. And finally, just a shot that I think emphasizes both how just incredibly slender these columns are and also how dramatically long this cantilever is. And I suspect it'll even look more dramatically long once the roof deck will go out to here, but then another couple feet beyond will be the finished roof surface. So I want to close just by briefly talking about Frank Lloyd Wright. It was in putting these slides together that I realized the 2 structural aspects that I struggled with and worked so hard on in the design of this pavilion were also 2 of the structural elements that I think throughout his career Frank Lloyd Wright made a lot of people nervous with and pleased by. Of course, on the left is Falling Water, where the cantilever is featured prominently. And again, we went to great lengths to make these cantilevers as long and slender as possible. But unlike this building, where the cantilever was probably near collapse when it was finally repaired a few years ago, I can assure you that ours will be just as strong as they are today in 100 years. And then finally, on the left is Frank Lloyd Wright's great workroom in the Johnson Wax in Racine, Wisconsin. And he envisioned these tall, slender columns, 21 feet tall, but design codes at the time didn't permit him to make something this slender. He wanted a 9-inch base, which wasn't allowed, so he rather dramatically had to conduct a full-scale test in which he was reported to have whacked the bottom of the column with his cane during the testing to convince authorities to have a variance. So just to give you some perspective, these columns had a height to depth ratio of about 29, and ours are at 65. So I think Frank Lloyd Wright would have been impressed. So in closing, I'll just quote Frank Lloyd Wright. Obviously he thought in part like a structural engineer, and as he looked back over his career, he noted the thread of structural consistency running through his work. And he also said that, so the poet and the engineer and the poet, both in architecture, may be seen here working together lifelong. And hopefully our work on this pavilion has achieved similar harmony. So that's all from me.
Good evening. I'm Bruce Nichol. I'm with Front, and we're the facade consultants for the project. And thanks to Dmitri. I'd like to pick up where Dmitri left off, and to reiterate something that Toshiko said about the way that we have worked together on this project. It really has been a collaborative process. And so when Front was brought on board, we were obviously subservient to Toshiko's overall design direction, and have to understand the sensibilities of her vision. For us, that primarily means encasing the building in glass in a minimalist way, long spans, with very little articulated detailing. And further to that, to work with Dmitri in pursuit of a very elegant structure which does not impose too great a load on the glazing, such that it can be executed in a minimalist way. So these are slides from my two predecessors, and they show what we have to take on board and what we have to do our own analysis of. This next slide shows how our own engineers would run their calculations on the building primary structure movement to see what loads would be imposed on the glass skin. Now, the early iteration of the glazing detail was to have the columns and mullions embedded in the glass, such that some of the load from the main building would be imposed on the glazing. This is neither ideal nor desirable from our point of view, because it makes us a little bit nervous about the way that glass is going to behave. I would suggest that for RE Krug Corporation and Tom Fleming, who's here tonight, that it's probably would make him quite nervous as well, because he eventually owns this, and we try to avoid imposing load from the primary building structure on the glass, because it's not very good at accepting that. It's just such a brittle material. But other challenges of this initial iteration are that you need to provide a soft joint between the glass and the structural steel to absorb that building movement, and you also need to separate the cold outer surface of the glass from the hopefully warm interior, so you want to avoid this thermal bridge. Now, the result of all of that buildup of glass and soft joints worked out at a little over 5.5 inches in terms of a sight line. So whilst proportionally that's not a very large dimension over the vertical span of the glass, it still becomes something quite large, and by divorcing the structural steel from the glass, we can avoid that build-up in sight line and get it down to something more slender and minimal. Now, this shows an initial analysis of that structural setup, whereby the steel column and mullion as a hybrid imposes bending stress on the base plate. So this is the kind of analysis that was done to show how those pieces of steel needed to be engineered under that scenario. And this is a thermal analysis to show that cold bridge, the transmission of cold from the outside through that glass and steel connection to the inside. So again, less than ideal, and that's at the jam condition. Now, what we've ended up with is something quite different, and you'll see it in the drawings that follow. But this is supporting the glass in lieu of having vertical edge support in the columns and mullions, supporting the glass at the base only and cantilevering it vertically so that the glass is clamped very rigidly at its base, and it spans vertically for over 15 feet. And this eradicates the need to have any vertical framing in the glass, but it does mean that you have to have a very special detail at the base, where in the triple glazed build-up, you'll see the 3 layers of glass with ½ an inch of airspace in between. Only the inboard laminated ply of glass is actually working structurally to support it. The whole triple glazed build-up is taking some lateral load from the wind, but the primary work is all being done by that inner light. And here we have it clamped in a steel clamp, a double angle system, which is the dark blue, and then the light blue is a grout which is poured in between and sets up hard. And that is typical in a balustrade design when you have a glass balustrade, but very few balustrades are 15.5 feet tall, so that's the special challenge of this project. This is our analysis of how the glass deflects. I'm not going to scare Mary any more than she's already been scared by showing it moving in and out, but just to reassure her that it is, by engineering, allowed to deflect its span over 240, which amounts to about an inch, and under our analysis these panels would only deflect by 3/4 of an inch under a 50-year windstorm. So you might perceive that in the reflection in the glass, but given that Toshiko designed out any coatings on the glass, there's virtually no reflection to perceive that. So under a 50-year windstorm you won't know what's happening. Now, this is the drawing of the glass assembly that we ended up with. So given that the glass is held, this is a plan view, and this is at the jam condition, glass to glass joint between panels, and then at the mitered corner. And it just shows how the triple glazed build-up of the insulating glass unit is assembled. This is the outside, and we have a lighter laminate to the outside for security, ½ inch airspace, a 1/4 inch of glass in the center, another ½ inch airspace, and then a heavy laminated build-up of 15 millimeters or 5/8 of an inch and 12 millimeters or around ½ an inch, because this laminate is doing all of the structural work. And then in between the glass we have an extruded gasket, and then a wet silicone seal to the inside and to the outside to make it watertight. And then in section, we've got that clamping detail again at the base, which is held down and bolted into the foundation. The clamp, double clamp there with its high-strength grout, holding only the inner ply of the glass. The center and outer plies are resting on an angle which is welded to that main clamp at the base, and then all of that is insulated and waterproofed to the exterior with the drainage there at the outside, and then the glass floor detail and the forced air at the perimeter there. And this is the stainless steel column in Eleanor is now separated completely. One thing that Dmitri talked about, which is quite spectacular in terms of the roof cantilever, is the dimension that the roof will displace under snow load, causing a positive displacement, or negatively under wind uplift, and that has to be taken up in the head joint. Now, all of the gravity load of the glass is taken at the base, but we do need to provide lateral restraint under wind load acting on the exterior, and that has to be restrained at the head. Now, that is why we have it clamped at the head, but we do need to release it, or have what's called a slipped connection, to allow the wind to, the roof to move up and down under snow and wind load. And initially this was done by slipping that connection at the primary structure. However, that requires very tight tolerance into the steel head detail at the top of the insulating glass, and that did evolve into a rather better detail which is easier to install. I don't know whether Tom again would agree with that, but this detail, by just providing an aluminium frame at the head of the glass, allows the roof to move up and down, the glass to stay where it is, and this space allows for the travel of the roof without the glass ever touching its surrounding frame. And you'll see that in some of the installation shots a little further on. Now, in order to get this glass fabricated, procured, we had to go to China because it's very rare to be able to buy this kind of glass in North America. There are very few manufacturers who can handle this size of glass, and because they have a virtual monopoly within northern United States, they can charge what they like for it, and they're not held to competitive quality control, so it's not always as good as we would like to see. For that reason, we procured the glass in Shenzhen in southern China, and Toshiko's team and Tom's team traveled out there to the factory to inspect the units once the first units, the first panels had been fabricated, and they did a quality control inspection to check things like edge seals, the silicon jointing, some of the structural silicon that holds the whole insulating unit together, to test for tolerance, blemishes, and really to inspect the quality output of the factory before any of that glass was shipped to North America. The same process was gone through on the stainless steel columns, which there you see ex-factory once they've been bead blasted and polished on their exterior. So the quality of workmanship that you see in this simple execution really belies the amount of effort that was gone through in terms of engineering and fabrication and checking and testing before the material was ever installed. And here you see the columns and base plates as they are installed on site with a protective wrapping, a plastic wrapping, which is yet to be taken off. So these columns have yet to be unveiled. But this slide shows the degree of tolerance, or lack of tolerance, I should say, in this construction. Because things are so closely juxtaposed, there's very, very little room for installation tolerance, for fabrication tolerance, for any kind of overlap. So in some cases, for the facade and the primary structure to pass so close together, things had to be trimmed down a little bit tight. As you'll see, some of the base plates there are cut off at their edge, but again, don't worry, Mary, it's all structurally sound. There's just no fat left in the system. And at the head as well, you can see the very tight tolerance in the steel construction there between the stainless steel and the mild steel as it gets bolted together. In fact, at the perimeter, the glass clamping system at the base, as it passes by these structural steel columns, had to be cut out around the base plates just to allow them to pass so closely together. And this again was executed very well on site. Now on the west facade there, with the concrete already cast in place, this was the first part of the glass to be installed, and you can see the crane at the top there, which was used to pick the glass after it arrived on site, swing it over the building and bring it to the west face, which is has restricted access. And once that glass was delivered to that site, it then has to be hoisted in using suction cups and a chain drive hydraulic hoist, which lifts it up onto this shelf on the concrete wall on the west side. And then Tom's team had to then maneuver it into place with very tight tolerances around this steelwork, set it in the base channel, and get the head aluminium cassette that you saw earlier aligned on the top. So all of this requires a lot of machinery, articulated booms, powered suction cups, and not a little blood, sweat and tears on Tom's part as well. And here you see his team working inside and outside just to get that finally set in the glazing channels at head and base. And you can see, you'll see this on many of these installation slides, the actual overlap of the glass, that's the inner ply that you can just see the bottom edge of there. The piece which is going to do all of the work is obviously exposed at this point and very, very vulnerable to damage, given that it has to come so close to hard materials which could shatter the glass. And at that point you have to scrap it and go all the way back to China. And it's quite remarkable and worthy of great credit to Tom's crew that they managed to install all of this glass without any breakage, or at least any breakage that he's confessed to at this point. And there you'll see that exposed edge as it goes into the glass clamp. These are the setting blocks which take the dead load of the glass, and as that goes into the two-part clamped detail at the base, the grout is then poured in around this exposed edge and sets up hard, and that's how the glass is supported and does all of the work. So that's the west facade with 3 lights installed in the center there early on in the construction sequence. And then on the other side they needed a slightly larger crane to hoist the glass onto the east facade. There you see the stainless steel columns in location waiting for the glass to arrive. The suction cups used to pick it right from the crate and hoist it into place. And there is the head detail. It shows you the proximity of the glass to the steel. So that's the kind of tolerance these guys are working with, down to, it was engineered as 3/4 of an inch, but came down to actually 1/4 of an inch in the worst case. And that is due to accumulative tolerances of the fabrication and installation of all the parts and pieces. So if you're last, and you're going in with the glass, you have what's left. and in some cases it was 1/4 of an inch that they had to play with. So by the time Tom's team has protected the glass with some insulation and plenty of duct tape and good wishes, there's very, very little room to slide that piece of glass in there. And here you see the glass being lowered in from the crane at the top with 2 guys on the hoist. And as that gets lowered in, in between the cantilevering beams, I should mention that the edge beam, which ties these together, had to be left out at this point to allow that glass to come in. It's lowered, rotated, and then set in its base and head. So here you'll see a little bit of the edge protection at the corners there, where it could quite easily shatter. And that is then what we call shunted into place. So it's set at a slight angle, lifted into the head, and then straightened and lowered into its base clamp position. And the protection is subsequently removed. So Tom probably has his hands over his eyes at this point. I don't know where he is, but tremendous job to get that all in there without damage. Again, the exposed edge. And Mary was asking me earlier today about how safe and secure this glass is. The good news is that once it's installed, it's very, very robust because it's a heavily built up laminated system. So the glass is all heat strengthened, it's laminated, and it's very, very difficult to break, even under heavy impact, missile impact load. It's almost anti-ballistic in its strength. But whilst it's going in, those exposed edges are very fragile and vulnerable to damage. And if you were to hit the exposed edge of that heat-strengthened glass with a hard object, a sharp object, say a piece of steel, a hammer, if you tap it on the edge, the whole thing will explode. So it's incredibly vulnerable in shipping and installation, but once it's gone in, on its surface, it's very, very hard. So I'm very glad and relieved that the last piece of glass has gone in, and it's now safe and secure. So these are more of the pieces being hoisted, some of the edge protection going on there as they're rotated and put in. And there you see the perimeter trim which is going on, and you see that slight gap at the head that we talked about earlier, which allows the deflection up and down and the snow and wind load of the roof to happen without touching the glass, and you'll never perceive that. And this is the edge seal with the silicon. Again, it's a very minimal joint in between the 2 adjacent panels of glass, and because the perimeter steel columns are divorced from the glass, the sight line of the glazed units with the column lines up, so you get now around 2¼ inches of a visual sight line in elevation, which allows for the optimum clarity of the glazed skin. That, coupled with the fact that we took out any of the surface coatings which can make glass appear slightly darker than it would. This is all low iron glass with no coating, so it doesn't come any clearer than this. It's literally museum quality glass. And there is the the final joint with the stainless steel column to the interior, and then the edge seals and spacers in the insulating glass unit, and that nice joint which is yet to be siliconed and made weather tight. And then finally the corner pieces were hoisted in the same way and brought in. You can see a corner going in there. Again, on one side of the corner, these are eccentrically sized panels. This is the larger piece of the corner going in, shunted in at the base and head and aligned vertically. That's set in its base clamp and finally manhandled into place. and you'll see the beautiful mitre joint at the corner, which when you go to the visitor center, once it's complete, and you look at that corner at 45 degrees, I think you'll appreciate the engineering and fabrication that went into making that a true mitre joint, which is absolutely minimal, as discreet as you could possibly get. A very successful corner. And then lastly, the skylights on the roof, which are quite a different system. This is extruded aluminium, captured on all four sides. Now this had to be a slightly different glass framing system, because as the glass moves from vertical to horizontal, its performance is far less in terms of its thermal transmittance. So there we went for four-side supported IGUs, which have a Lowy coating on them in an extruded aluminium frame. There you see the frame open, the mullions in place on one side, the transoms about to be lifted into place. And there are the edge seals, the edge of those skylights from the outside, which are then gasketed and siliconed into place. That's all of the glass in place, a view that unfortunately you won't see. And then the pressure caps which go on from the outside to capture that glass and hold it in place. And there you see the thermal insulation within that perimeter frame to keep the whole system warm, because obviously the majority of the heat will escape from the building through the roof. So this has to be better performing than the walls. And that's as the glazing is completed. Not, Tom, designed as a walkable surface, but I can see that your means and methods are your own business, and so long as none of your workers landed on the floor of the museum, then that's fine. So that's as that was completed and all successfully done. So I'll hand over to Paul, who's going to talk about mechanical systems.
To say I've truly enjoyed working on this site over the last 6 to 7 years. I had the fortune to start working on the Frank Lloyd Wright Martin House back in the beginning of, I guess it was phase 3 at the time, and I was involved with the carriage house on site and the reconstruction of that, and then was fortunate enough to be able to join up with Toshiko and Front and SOM to work on the visitor center. But I have to say that this building has presented a number of engineering challenges when it comes to systems on the interior. And while SOM structure is visible and part of the architecture, as is Front's glass work on the exterior, nobody wants to see my systems. And nobody wants to hear my systems. Yet this building is all glass and provides a very poor acoustic environment. It's a glass structure, it has a concrete floor, and it has drywall ceilings. And there's nothing soft within the entire building. On top of that, glass is not the best insulator, even though we have a triple glaze, which makes the thermal properties extraordinarily good. But the Buffalo climate can be very cold, so we needed to counteract any potential thermal losses through this glass structure. And glass also allows intense sunlight in, which in the summer times you can end up with extreme solar gain on the building, which adds to your cooling loads. Now, on top of those three things, we had a client that needed a very flexible building. And when we were talking with Mary originally, she was saying, okay, well, we need a building that under normal circumstances is just comfortable. But then we also want to be able to put up to 220 people in there for an event. And we may also want to make it a museum space for artwork sometime. So we all of a sudden, we have to have a system that allows us this great flexibility that fits into the glass building, and it's also on a historic site. So we are not allowed the benefit of having any exterior equipment, such as heat rejection, such as a cooling tower or a condensing unit out on the site. And to go through the building systems, I felt it was best to show you a cross-section of the visitor center as it is. Where's that? There it is. Thank you. This is a cross-section looking from the south towards the north, and I wanted to go through the building bit by bit on how we addressed these challenges that were posed to us. And I'd like to start with the radiant floor that Toshiko talked about before. And now in the wintertime, we have a radiant heating system that's installed below the slab and takes care of the primary heating load for the building. It takes care, it adds to the occupant comfort. It helps reduce the amount of airflow that we need for to the system to only accommodate a building pressurization and then code required ventilation from outdoors. And by reducing that, we can reduce our fan speed a lot and increase our energy efficiency. Now, by having this radiant system, we also are allowed to do what people are apt to call radiant cooling, but I prefer to call it radiant heat absorption. Because essentially what we're doing is, as the exterior sun comes in and warms this floor up, we don't want it to then radiate into the space and add to our cooling loads. So what we do is we can run a tempered water through the radiant slab and draw away that solar heat and put it back into the system and take that load out of the equation when we're dealing with the building. So essentially what it does is it takes our glass building and it eliminates the solar portion, it eliminates the glass load, which is huge when we're trying to design a system because it allows us to reduce that size and make everything a lot more energy efficient. The next portion that I'd like to talk about after the radiant slab is also has to do with the solar aspects. But it has to do with some automatic shades that were designed into the project from the beginning. On the interior of each piece of glass on the east and south and west portions of the building, there's an automatic light sensor installed in the center portion of each span, and these shades automatically raise and lower to take out that morning glare as the sun comes up from the east, or the late night glare that can come in from the west. It's not so much of an effect in the middle of the summer at noon, because of the way Toshiko designed these overhangs, what they call the angle of insolence, which is the angle the sun takes towards the earth at this latitude, places the sun at a very low angle on the glass. So the building design in itself acts as a great shade, which was very much in line with Wright's cantilevered buildings. In addition to dealing with these solar loads, we had a great deal of challenge with engineering acoustics. And we focused our acoustic work and absorption on the ductwork below the floor slab. We started off by slowing the air down at all of the air outlets. And the air outlets surround the perimeter of the building, and there's separate branch ducts. As you can see, each one of these it's an oversized outlet, so the air moves very slowly through these under normal operating circumstances, and the low velocity helps us reduce that outlet noise that most people are so accustomed to with an air system. In addition, we had each one of these branch ducts that feeds the perimeter has a balancing damper. But balancing dampers historically have a great deal of noise associated with them as they are adding resistance to the air. And as they add resistance, they're closing, and you get a lot of air turbulence around them, which causes noise. That air noise gets absorbed by two elbows, which were designed in, and we did go back and forth a number of times with the contractors, who eventually relented, but they're questioning why they couldn't just do a straight run into the duct here. But what we're aiming for with this is a user experience, a visitor who can go in and enjoy the architecture of this building without having to combat an air noise from around or see where these systems are. We don't want them to impede on the user experience at all. And we love this picture. And unfortunately, the floor of the building isn't glass as well, so you can see all this going on below, because it's my favorite part. But this picture is maybe about a week before the pour. So unfortunately, all of this is covered up at this point in time, but it's a great historic record of what was installed below. And each one of these ducts is a double wall. It's perforated on the inside, and it's got an acoustical lining between the two pieces of duct. I've got a better picture later. And then this exterior coating it's sealed with PVC. And what that does is it really increases the lifespan of this ductwork, so the building won't outlast the ductwork. So we're looking for the long term with these types of systems. But you can see all these elbows that were installed. You can see the scale of it by this person who's standing next to some of just the branch ducts. And unfortunately, this picture doesn't show someone standing over here, but these ducts coming through this area are about 42 inches in diameter. Focusing in on this area, and there we've got an interior shot that I took, inside one of the ducts. And what you're seeing is the interior perforations, which absorb fan noise all through the duct system to avoid transmitting any of that into the space. The systems, the air supply into the space is critical to the overall aesthetic to the visitor. And as part of hiding the systems, the supplies are integrated into the architecture. And Toshiko designed a continuous grill that runs around the interior perimeter, the interior of the perimeter columns, all the way around the building, and it serves as both an uplighting source and a supply source for all the ductwork. But at the visitor, it all just kind of disappears into a seamless integration. The other thing is the airflow is very slow here, and as the air enters into this space, you end up with a stratification across the top layer. So down in the area where the occupants are, the temperature is just perfect for occupant comfort. But up in this upper area, it can be warmer, and thereby increasing the energy efficiency of the system. We had to, as the building didn't allow us much space for ductwork, grills, or anything, we used the top of this west volume as the return area. So above this, there are numerous large openings that are completely out of view from the visitor and completely out of hearing from the visitor because of their size. So the air slowly enters the space from here and slowly leaves the space from here and back down into the mechanical space. Other systems are hidden up through these main four columns. So, as tying back to what Toshiko said, Wright wanted every building element to serve multiple purposes. And these columns not only serve to draw the user's attention to the center of the building and support these large cantilevers, but they hide our plumbing, plumbing drainage from the roof. They hide our fire suppression system, and they hide electrical conduits running up in a seamless fashion, so there are no other penetrations up through the building except for these 4 columns. Now, the other main portion of this building is that the entire heating and cooling system is run on a geo-exchange system, which passes heat to the ground in the summertime during heat rejection and cooling, and draws heat out of the ground in the wintertime for heating. And that takes care of all of the air systems and all of the radiant systems. The geothermal system, we ran into some problems on site, and these geothermal tubes run down 350 feet into the bedrock of the site. And there are 15 for this building, and I believe there's another 36 for the rest of the site. So the entire site will be on geothermal. It allows us to install systems out of view from any visitors, and maintains the clean site plan that was Wright's initial intention. The last thing I'd like to touch on is just that with the system flexibility, to accommodate that, we ended up deciding on using a single central air handling unit rather than multiple fan coils around the perimeter, which allows us flexibility with airflow from a very low airflow with minimal occupancy up to that 220 person event where we have full outside air and high volumes. There's a hot water reheat system which is incorporated, which allows us to do dehumidification for a museum environment if the client so chooses in the future. And there's chilled water cooling that's we're converting geothermal energy into chilled water and then using that chilled water to get extra cold air, which allows us to do all of these functions at the same time. And the building, we have a number of systems that are incorporated green technologies. And as a panel, I'd like for us all to discuss how the building holistically brings a lot of green technology to the table. I'd like to start that discussion with just touching on a couple things that are in the systems. The first one is indoor air quality for occupants and for the visitors, and we have a very high filtration system on this air handling unit, which removes all the particulates and pollution and pollens from the air and maintains a very clean environment inside the visitor center. All of the occupancy, the outdoor air and ventilation load is controlled based on CO2 sensors. So the building monitors the level of CO2 produced by the number of people inside the space. And as the CO2 level rises, it says, I need more outside air because I need more oxygen. These people are falling asleep. So it starts pumping in more outside air, and it increases how much air is exchanging through the building. And then as people leave, the CO2 levels then go back down, and the building can slowly close the outside air intakes, and thereby only using how much energy it needs for that particular moment. There's also an incorporated outdoor air economizer into the system, which allows, when the outdoor air temperature is right, the building will just turn off the systems and just bring outdoor air 100% in, and it's like opening the windows. So we have this glass wall that we can't open the doors, but the building can say, hey, it's really nice outside, let's open the windows and let in that outside air. This radiant slab that's installed allows us to run the main fan at a much, much slower speed than a normal building would. And it absorbs a lot of the heating load, a lot of the cooling load in the summertime, and it takes up most of the heating load in the wintertime. And reducing the fan speed increases energy efficiency and increases the comfort because you don't have drafts blowing across occupants. And you also end up with the stratification, as I mentioned earlier, which involves, which allows multiple temperatures within the same building, and also reduces the energy costs. And the last mention was on the geothermal heating and cooling systems that allow us to utilize the ground for our heating and cooling, and in normal operations we can greatly reduce the energy costs of operating the building. And I'd like to continue this discussion. We're going to bring up we're going to put up the screen and bring forward a table and do a panel discussion with all of us up on the stage, and do a mediated question and answer session.
Raising issues about the project? Yeah.
Toshiko, this is not the first presentation I've heard of this phenomenal. Congratulations to everybody. As much as it's 21st century and as cutting edge as it is, I'm wondering, I remember in an earlier presentation that you discussed a roof system that was perhaps even more ambitious than what existed on site, and I wonder if you could tell us a little bit about the history. I remember maybe your earliest presentation, early 2004, which described a shell that was almost analogous to a hollow canoe or something like that. Was that an early part of the thinking? I can't remember, but it struck me.
Yeah, exactly.
Can you please repeat that question or summarize it?
Yes, his question was as follows. He remembers my very early iteration of a roof, which was conceived as a hull of a boat, as if made by some kind of composite fiberglass or carbon fiber or something, as a single unit. And he's absolutely, you have a great memory. That's my intention when I first designed this building, and it was possible. And idea came from a fact that all the trustees were saying, when you do this building, there's one thing you don't want to do that Frank Lloyd Wright was famous for. It was that his buildings are famous for leaky roof. So I said, if I made a roof like a boat of a house that goes in the water, it would be leak-proof. So ideally, it was I would have this made up in a boat shop in Bristol, Rhode Island, a guy who makes a hull of America's Cup boat and brought in through the Great Lakes or something, go up the Hudson, whatever, and then just plunk it on top. Well, there's a familiar phrase that's called value engineering took place. Well, it is expensive. It's very expensive. And then also, when you look at work with boat builders, I have really done a lot of research with that. And I kept telling boat builder, this is not racing in like America Cup's race against Team Prada. It's sitting in Buffalo. But he couldn't also make it low tech enough. So this is made like, it's really made to race, but I didn't need a roof that can raise just sitting in Buffalo. So there's a disjoint between the cost and technology, which is too highly developed. But I think it's in the process. Probably this fiberglass and carbon fiber is very expensive. It's coming to may be able to, but again, issues of cost and efficiency, as we all are interested, that's the result. But conceptually, I'm glad you remembered this, because that was the concept behind it.
So there's a question. Yes?
Why did you decide not to coat the glass, and how will that affect artifacts that you might have that will be ultraviolet light sensitive in the exhibition space?
So I maybe answer first and then well, one of the idea is clear is that we really want to have a transparent glass so you can see right through without coating. And one of the issue of a coating is heat gain and then glare, which is taken care of by automated shading system. So that's the care of it. Now, in terms of exhibition we are preparing, we will not have any artifacts. That's one of the premises of the program, to have, it's going to be all reproductions. And then artifacts that's going to be, we will not have any original item, which is ultraviolet sensitive. So that's actually the premises that, so there's a balance between those two, which made it possible. But then if we did have ultravioletly sensitive, we could take care of that within the case design. We'll put a case which protects the artifact, and we can control it that way. So that's how it has evolved. Would you like that?
Just one thing to add to that is that the glass coating, low emissivity coating that's traditionally put on the glass is beneficial in cutting down the solar heat gain, but the harmful UV spectrum of light that can damage and fade finishes and surfaces to the interior is largely blocked by the polyvinyl butyl interlayer that actually glues the laminated glass together. So that is still present without having a coating on the glass.
How do you control the acoustic echo inside the building?
I think that's
my things. Well, we don't know quite, but it depends on how many people there is. Of course, there's more people, more conversations. There'll be going to be more lively atmosphere, and we don't think there's a reverberation that's happening there. But if you have 200 people and having a dinner with loud conversations, there may be more what I call a lively atmosphere. So that's. But when you have occasion like that, you will have tables and then chairs, upholsteries and tablecloths. There will be and people wearing clothes. So there's hopefully no naked people in there. This does strangely add to the absorption. So it will be a balance of that.
Yes.
The lighting, so you'll have lighting from the floor up to the ceiling.
Yes.
And how will you light the objects?
The it's all artifacts are lit within a case. Lighting is embedded in the case themselves. So again, it's an idea of sustainability. Like we don't want to be lighting a ceiling where nothing is happening, but we really want to have a focus on artifact itself. So it's really more like an idea of task lighting, and then more of an indirect lighting combination thereof.
Okay.
Yes.
The facilities that we're going in the basement, where are they going to own it? The basement was originally planned.
Yes.
Longer, so where are those
Basement had exhibition spaces, so many of the exhibits are integrated now into the ground floor. Scope of work of exhibit, extent of it has been cut down, so it's less exhibit than planned before, but now, before there was no exhibition on the ground floor level, but now the ground floor level acts as a visitors' introductory and gathering space as well as exhibition space. And also, there is a basement there below West Volume, which has all the mechanicals. Right.
Yes.
Going along the line of the same question, is that another example of value engineering, number one? And then number two, without the need for that big stair that was down the middle of it, I would think that you're really not losing that much exhibition space. Am I right?
In terms of square footage, we lost it, but in terms of efficiency, we probably increased it. So, and also it was big. It will be very nice to be able to go down to the basement to have a series of exhibit, but we realized that for this particular site, the main event is a Darwin Martin House. So if people come to visit, they would really want to know the background information. They'll be in a hurry to want to go see the main event. So I always consider this visitor center like a bridesmaid to the bride. So in a sense, it's actually experiences. I think there's enough information that's visitors oriented, but I think it's the kind of facility which really is enhancing the main experience. And it is smaller, it doesn't have a basement, but I think it works as a better member of a team of other building compounds in the entire site. So it works better with the rest of the building, Carriage House, Conservatory, Darwin Martin House, and Barton House. It really works as a team member more, rather than isolated another building. So
I think that, don't you agree that the tighter the restraints in a project like that, often the solution is even better than when you get started?
Yes, I think all my trustees would really agree with that.
Kelly.
The title of this was Integrated Design. I'm wondering what you all feel is the best gesture of integrated design in the building, and maybe what do you think is probably the least successful element of integrated design?
Somebody else. What do you
So I'm going to pass the microphone to the engineer at the end here to start. Just, well, you have the microphone, make sure.
Well, in terms of structure, I'm quite proud of the fact that our columns, the form of our roof, and the shape are in no way hiding. What's doing the work and holding up the roof is what you see, and hopefully appreciate the way it looks and adds to the total aesthetic of the space. And even though the roof beams are covered, the basic shape and form that the final finish will have follows that basic structure. So really nothing is hidden. So from a structural engineer's point of view, I'm biased toward that, and I think that's very successful. What's unsuccessful structurally? I guess you could make an argument that everything in the world is a trade-off. So when you minimize one thing, you maximize something else, and that's just the nature of the world. So for instance, the columns, if you wanted to be a critic, and you were talking about structural economy, a solid steel slender column, it weighs more and is more expensive than a structurally optimum column, which would be 2 feet in diameter and have a very thin wall. So it's not perhaps, I mean, it can't be all things at once, and so we've given up cost and efficiency of pure material for minimization of how thick it is. And I think that's a good compromise, but you could make that argument if there was a scarcity of stainless steel. We used a little too much of it for that. But
I'd like to add to that well, I have a hard time thinking of what is the best example from this building of integration between engineering and architecture, because as the building has progressed and the design has progressed over these past few years, and things have constrained us from either site conditions or material availability or construction cost, the building has become more streamlined, and I think it works. Everything's been reduced down to its necessities, and therefore, as a whole, I mean, everything's very, very complementary. The structure it allows us to have these great open spans, and while the glass allows us to maintain this thermal envelope with and barrier between inside and outside, while allowing the visitor to view the site like they are standing outside. So I think everything's just kind of been meshed together very well over this process.
I would agree with that and say that the mark of the success of integration is that you can't really see it. Somebody mentioned today that there could be no competition with the Darwin Martin House in the visitor center. It's there in service of Wright's architecture. However, when you look very closely at the details, and particularly an educated audience such as yourselves, when you look up close at how the visitor center was achieved, I think there's so much intelligence in there in the way that it was fabricated and put together that it does provide some competition to the ingenuity of the Darwin Martin House of its time. So I think that is the success, is that it's all in there, but it's invisible. I think if there's any aspect of it which is perhaps unsuccessful, it's that, as Toshiko mentioned earlier, there were some technologies that we would have liked to have brought to the project that we were unable to, but those things are for the future.
For me, I think that Jack said it's 5 years. We all aged somewhat. And what provided us was very extraordinary. When I think of buildings, there's three aspects: time, budget, and quality. And then usually if you rush too much, it becomes expensive, you don't get a quality. And then if you don't, if you don't spend enough money, it affects schedule and then quality. There's balance between them, but this 5 years was a great gift of time, although it was not necessarily always a peaceful time, but going through different iterations and so forth. But through that, I think we went through refinements. So in a sense, it's not one design which is we just did it, this is good and this is bad. It just went through a lot of 5 years of refinement and rethinking and streamlining altogether. And as the budgets has gone through fluctuations and the size of buildings, so we kept refining it. So we came to the point in which we have what I call optimum building right now. So when you talk about optimization, it's much more holistic idea. It's just no one over the other, I think, which is in what you call equipoise, which is also a phrase that Frank Lloyd Wright often used about sense of equipoise. So we think there's a balance in what we are doing, and one not having all the mechanical systems and facade systems and architecture and structure kind of balancing out with each other. So if I may say so, we're in a very good place in optimization.
So the last question from Mr. Quinlan. Yeah?
Some of the language I'm hearing here is reminiscent of Mies van der Rohe. And I'm wondering if you could comment on the notion of refinement and refinement that you're talking about vis-a-vis Mies and the refinements of Tugendhat and Seagram and buildings like that.
Well, then, of course, Jack challenges me with the most a difficult intellectual question of all time, in which I have to define Frank Lloyd Wright and Mies van der Rohe. Essentially, what's the difference is kind of a story, and how I interpret the relationship, and I can give a 2-hour lecture on that. But at the same time, what's interesting about Mies van der Rohe in refinement is about minimalization, economization, optimization, but there's a element of abstraction reduction, which I think Frank Lloyd Wright never reduced it. It's always increased it. So for me, intellectually, the challenge is how to make a minimum statement, but it has more values and it has more meaning. It's just not what the glass is. In a sense, it's more about, how do you say, arriving at a complex building with a simple architectural act. To me, that's really Frank Lloyd Wright, because he's such a complex, rich, he's broad in references from human nature to comfort level to how people lived, and all that's integrated in his thought process. So of course, when I do a building which uses steel or glass, I think of how do I differentiate so it doesn't simply become a glass box and then it just considered to be dismissed as a Miesian glass box. How do I actually make it closer to the idea of Frank Lloyd Wright? And you just put a nail on the head as an architect. That, to me, is a line I have to keep on going, and that's why the very complex and rich involvement of consultant was absolutely necessary. I don't think that that happens in museum buildings, this kind of complexity and richness and meaning derived from a simple detail. But
thank you very much. It's great. No, it's great.
How about another question? How about another question?
Can I ask one last question? Watching the presentation, it was, of course, amazing technology.
Please speak louder.
I'm just curious if the panel would have a consensus on how far back we would have to roll the calendar before we get to the point where we couldn't build a building like that based on how it was presented or the technology.
Do you want to?
I'll start from my point of view. The question was, and correct me if I'm wrong, that what came across was the refinement and complexity of this building, and how far back in time would we have had to go when such a building would not be achievable. And from a structural point of view, I could say that the basic physics and mechanics that determine how small and how efficient all these members can be were established probably in the early part of this century. But it's only recently that we've had the computational tools to practically refine the structural design. It would have taken an army of engineers, a year of calculation to refine something this carefully, and something I can do in an afternoon with computer software. So it's not that it wasn't possible, it's just incrementally it would have gotten less and less likely that anyone would have had the wherewithal to pursue such a large computational task. So I would say the last 20 years ago would have been very unusual. Very few firms had this sort of software that made this easy. 10 years ago, unusual, and now a lot of firms have the software, but I think only few are confident enough to and have the time and budgets and experience to really push it. So it's a sliding scale, but 20 years ago.
The other thing I would say about that is I think that, what's been demonstrated tonight is actually the willingness to use those technologies together. That I think it's not just a matter of somebody looking at the size of a piece of structure, but also thinking about the way the building is going to perform and predict the way the building is going to perform. And I think that, that takes a certain willingness on the part of the design team, and particularly on the part of the architect, but actually in terms of just the way of working. So I think, and I think that's also relatively recent. And perhaps that way of working has been encouraged by the development of the technology over the last 10 years. But
Would anybody else?
I'd like to add to that, and I think the key technology that is the computer, and that's changed everything. And as the years pass and our computational abilities help us with our calculations, they help us do our calculations faster and more accurate and run models under different scenarios so you can try and understand what this how this building is going to react long into the future, so you can be more confident in your design. And on top of that, with this, from the systems approach, this building has a brain, and not that it thinks, but every little aspect of the systems is controlled and monitored and very precisely adjusted so that occupant comfort is optimal and the temperature is optimal and the energy efficiency is optimal throughout the day and the year. And that, while they were building automation systems 20 years ago, they have come far in advance. And I think maybe about 5 years ago, the technologies would have been such that we could do what we're doing right now.
So I'd like to thank on everybody's behalf the speakers tonight. I'd like to thank Mary for being so patient with this sort of truculent idea about doing this thing. And I think the other thing that, you know, is really, I hope, helpful about this is that the presentations really showed you the building in ways that you'll never see it ever again. And that it is that intricacy about architecture and engineering, about art and science, which is embedded deeply in this building. It was embedded deeply in what Wright talked about. And I think that there's an extraordinary achievement in terms of really reinterpreting that, but respecting those disciplines. And I'd like to close just by quoting from this super book, which many of you know, a piece written by Rainer Banham, who's, you know, such an inspiring critic, who wrote about about architecture and the built environment. And in the first paragraph of his essay, he says, "This book is intended to make it impossible ever again for anyone who cares about architecture to say, 'We drove by Buffalo on the thruway but decided not to stop there because there's nothing to look at, is there?'" And so, again, I think we should reissue this because there's clearly a lot of things that we're going to want to stop and look at. And I'd like to thank everybody very much for coming tonight. Thank you.
Thank you, Brian.
Thank you very much.
Great idea.
I mean, it's amazing, isn't it? This happens so rarely.
Yes.
You know, I mean, it's like, this is like a school of architecture from the public here. You know, there's sort of level of things that people have heard about today. You know, not many people left, not a lot of these people.